So what if the multi-million-dollar large language model you're training right now is spending like half of its computational capacity just talking to itself?
I mean, it sounds completely absurd when you frame it that way, but
Yeah.
when you look strictly at the linear algebra happening under the hood of standard architectures, that is exactly what the data suggests is going on.
Right, which is wild. Welcome to the deep dive, everyone. For those of you listening, yeah, the machine learning practitioners, researchers, the engineers optimizing these massive pipelines, the standard transformer architecture is, well, it's practically dogma at this point.
Yeah, it really is. It's the unquestioned baseline.
Exactly. You have this very deliberate interleaved division of labor. Self-attention layers are designed to handle context aggregation, right?
Mm.
They look across the sequence, mixing information between different tokens. And then the feed-forward networks, the FFNs, they step in to handle the position-wise feature updates.
Right, mixing information across the channel dimensions. That is the canonical theory anyway. The attention mechanism looks outward to the context, and the FFN looks inward at the token itself.
And that theoretical pipeline has basically been the backbone of every major breakthrough since attention is all you need.
Pretty much, yeah. But today, our mission for this deep dive is to critically examine a new paper out of Apple by Shuangfei Zhai. It's called Exclusive Self-Attention. Because, well, this paper systematically proves that this elegant division of labor it's actually breaking down in practice.
It's totally breaking down. So we are going to unpack a hidden pathology in standard self-attention, look at the mathematical proof of what they're calling attention similarity bias, and then discuss how a really basic geometric trick, literally like 2 lines of PyTorch code, can fundamentally eradicate it.
And we are not just talking about toy models here either. We're looking at empirical performance gains across models scaled all the way up to 2.7 billion parameters. But to understand the solution, we really have to deeply understand the diagnostic first. We need to expose the bias.
Right. Let's get into the pathology.
Yeah.
Because if I'm building a model, my base assumption is that the residual connections are already doing the heavy lifting of carrying a token's current state forward. Like the residual stream bypasses the attention block entirely and carries the point-wise information directly to the FFN.
Exactly.
So the attention block should be purely dedicated to pulling in new context. It shouldn't care about itself.
That is the assumption we all make. But to test if the attention layer is actually sticking to its job, the author ran this really fascinating empirical diagnostic. They took a standard 1.3 billion parameter language model.
Which was trained on, what, 100 billion tokens?
You're right. Yeah, 100 billion tokens. And they analyzed the internal representations layer by layer across thousands of random training sequences. And 3 very specific, very alarming trends emerged from the matrices.
Okay, let's walk through those. What is the first anomaly they found?
Well, the first trend is that within the same attention head and sequence, the value vectors, so the V sub I and Vs sub j across different positions, tend to be highly positively correlated.
Okay, so the vectors that are supposed to contain the distinct content of each token are actually just pointing in roughly the same direction.
Exactly. They aren't as distinct as we thought. The second trend appears when you look at the attention scores themselves. So the diagonal values of the attention matrix, which, represents a token's attention to its own exact position.
The sub I comma I.
Yes, exactly. Those diagonal values are unexpectedly high. So the model is overwhelmingly looking at itself rather than searching the surrounding context.
Which logically leads to the third trend, which is just the absolute smoking gun here.
Yeah. It really is. When you measure the average cosine similarity between the final aggregated attention output, the y sub I, and the original self-value vector for that same position, the v sub I, it is extremely high.
Wow.
And it gets worse. That similarity actually increases as you move deeper into the network's layers.
Okay, let me try to put this in terms of signal processing, because this is just, it's wild. It's like having an incredibly expensive, highly sensitive noise-canceling microphone array. Right, that's your attention layer. And its only job is to capture the ambient acoustics of the room.
Right, the outside context.
But instead of isolating the external environment, it's just picking up the hum of its own internal battery. You're basically paying a massive compute tax just to amplify a signal you already have natively sitting on the residual stream.
That is actually a highly accurate way to visualize it. Geometrically, the network is using the attention mechanism to output a vector that aligns heavily with the token's own value vector. So it is burning finite representational capacity to model pointwise features.
But wait, why would the network even learn to do this? Like, if the residual stream is right there, carrying the exact same information straight to the FFN. Why is the attention mechanism duplicating the effort? Is it just some weird optimization artifact?
It mostly stems from the fact that standard self-attention lacks any structural constraint to prevent it from happening. I mean, gradient descent finds the path of least resistance,
Sure.
right?
Always.
So if reiterating the self-value minimizes the loss slightly in the short term, the model will just do it. It'll do it even if it cannibalizes the capacity needed for, complex long-range contextual routing.
Oh, I see.
Yeah, and this overlap in duties diminishes the FFN's specialized role, and it severely bottlenecks the attention head.
Okay, so we have a clear diagnosis of the pathology here. We have an attention similarity bias. The attention output and the self-value vector are uncomfortably aligned. But since the problem is defined geometrically, the solution must also be geometric, right? We need to force the attention mechanism to look exclusively away from itself. But how do we actually do that without, rewriting the entire fundamental architecture of the transformer?
Well, the mathematical intervention proposed in the paper is called exclusive self-attention, or XSA, and the formulation is incredibly elegant. You basically take the standard attention output, the y sub I, and you explicitly subtract the projection of that output onto the self-value vector, v sub I.
Let me picture this so we aren't just reading raw math on an audio deep dive.
Yeah.
Imagine the vectors in a physical space. The current attention output is essentially casting a geometric shadow over the self-value vector, like they're pointing in somewhat similar directions.
Right, they're not orthogonal.
So XSA is calculating the exact size and direction of that shadow and then just cutting it out.
Precisely. You calculate the dot product of the attention output and the self-value vector, which gives you the scalar magnitude of that overlap. Then you divide that by the squared L2 norm of the self-value vector and multiply that scalar back against the self-value vector.
And that gives you the exact projection.
Exactly. Then you just subtract it from the original attention output. So z sub I equals y sub I minus that whole projection term.
Wait, hold on a second. If I'm following the tensor operations correctly here, this isn't some massive architectural overhaul requiring custom CDA kernels. This is literally just Graham-Schmidt orthogonalization happening on the fly.
You've hit the nail on the head. It is just an orthogonalization step.
That's crazy. You are explicitly forcing the context vector to be perfectly perpendicular to the current token's value.
Yes, it mathematically guarantees that the final output vector is completely independent of the self-value vector. The component pointing in the same direction is zeroed out. The attention similarity bias is completely eradicated by design.
But, thousands of researchers have been optimizing transformers for years. You're telling me Apple drops a basic Graham-Schmidt step in the attention block and beats standard, highly optimized attention. What does the implementation actually look like for the engineer, the person writing the training loop?
Because you're the one staring at the code base, you will appreciate this. It is literally 2 lines of PyTorch code appended to the standard multi-head attention module.
Just 2 lines.
2 lines. First, you normalize the value tensor along the last dimension. Then you calculate the projection of the attention output onto that normalized tensor, and you subtract it. That's it.
That is unbelievable.
Right. No new learned parameters, no complex routing algorithms, just a deterministic geometric constraint that forcefully reestablishes the division of labor. The attention layer is now exclusively focused on contextual information.
Okay, I have to push back here. A theoretically elegant, geometrically sound trick is fantastic on a whiteboard. We all love those. But as we both know, the graveyard of machine learning research is filled to the brim with mathematically beautiful ideas that totally tank hardware utilization.
Oh, absolutely.
Like if this requires heavy reductions or strange memory access patterns that slow down the forward or backward pass on a GPU, it's totally useless in production. Does this theoretical purity actually survive contact with reality?
Let's address the computational elephant in the room, because it is exactly the first question any systems engineer is going to ask. They benchmark the time and memory efficiency of an attention block with XSA turned on versus the standard baseline.
Okay, what hardware?
They ran this on an NVIDIA B200 GPU in bfloat 16 precision, and they scaled the sequence length all the way up to 16,384 tokens while varying the model dimensions.
And what was the overhead?
Yeah.
Because orthogonalization usually isn't free.
The overhead is completely minimal. The forward and backward time in milliseconds and the peak memory usage in megabytes, they track the standard baseline almost exactly.
How is that even possible? We are adding operations to the hottest loop in the entire network.
Because those 2 extra lines of PyTorch, the normalization and the subtraction, They are entirely element-wise and reduction operations along the feature dimension.
Ah, I see.
Yeah, modern hardware, especially tensor cores on a B200, executes these types of operations with negligible costs compared to the massive matrix multiplications happening in the attention projections themselves.
Okay, so it's virtually free on the hardware side. That's great. But we really need to talk about the actual learning dynamics. Faster compute doesn't matter if the model doesn't converge as well.
Right. So the paper details extensive training runs using the NanoGPT codebase on the FineWeb 100BT dataset. We are looking at 100 billion training tokens across 3 specific model sizes to observe scaling.
Which sizes?
A zero point 0.7 billion parameter model, a 1.3 billion parameter model, which is a 1.4 billion config, basically, and a 2.7 billion parameter model.
And the loss curves.
Across all 3 model sizes, from the very beginning of the 200,000 training iterations all the way to the end, XSA maintains a clear, consistent margin over the baseline. Both training and validation loss are demonstrably lower.
Okay, lower loss is a good proxy, sure, but downstream task performance is where the rubber actually meets the road. A model can overfit to its own pre-training distribution and show lower loss without actually getting smarter.
True, very true. To validate that, they evaluated the final checkpoints on 8 distinct downstream tasks. We're talking about IRC-Easy, BooQ, HelloSwag, Lambda, OpenBookQA, PIQA, Socially QA, and Wino Grand.
So a really broad spectrum.
Exactly, covering language modeling, common sense reasoning, and knowledge retrieval.
What's the delta? And more importantly, does the improvement favor certain types of tasks over others, or is it a general gain?
It's a general gain, but the critical insight here is actually the scaling behavior of the average accuracy delta. For the 0.7b model, XSA provides an average accuracy gain of plus 0.26 over the baseline.
Which is modest. I mean, it's positive, but you wouldn't rewrite your entire stack for a quarter of a point.
Right, but look what happens when you scale up the parameter count. For the 1.3b model, the gap widens to plus 1.03.
Oh, wow.
And for the 2.7b model, XSA outperforms the baseline by an average of plus 1.36.
Okay, that is significant. Let's unpack the implications of that scaling trend for a second. It means XSA works exponentially better as the model gets bigger. Why? I would argue it's because the redundant self-projection in standard attention acts as a percentage tax on your representational capacity.
I completely agree with that assessment.
Think about it. If you have a massive 2.7b model and the attention heads are wasting, say, 20% of their bandwidth echoing the residual stream, that is a massive amount of parameter capacity just evaporating into nothing.
Right.
By mathematically freeing up that capacity, the attention heads in a larger model have far more raw representational power to dedicate strictly to complex contextual routing and reasoning, the architectural efficiency compounds.
Exactly. You are unlocking capacity that the model already possessed but was just entirely misusing. However, I know you usually look for the catch.
Always. I want to bring up robustness next. Because sometimes you see a paper where a trick yields a plus 1.36 gain, but it only works if you find the exact right learning rate to like 5 decimal places. If you deviate by a hair, the model diverges and the gradients explode.
Yeah.
Does XSA make the training dynamics brittle?
The authors actually anticipated that exact skepticism. They ran a robustness check, specifically evaluating the 1.3b model across 4 different learning rates, ranging from 1E4 up to 6E4.
And did the margin hold?
It did. The training and validation loss margins between XSA and the standard baseline remain near constant across all of them. The model didn't diverge once. It proves this is not a hyperparameter fluke. It is a fundamental structural improvement to the architecture.
Okay, so we know XSA scales beautifully with model depth and parameter count. But if you're an ML engineer today, parameter count is only half the battle. The other dimension, the one that's notoriously agonizing for standard transformers, is sequence length.
Oh, absolutely.
As we push towards autonomous agents, retrieval augmented generation, long document reasoning, context windows are just exploding. How does mathematically orthogonalizing the context impact long context modeling?
This is where the results transition from interesting to, frankly, highly compelling. They ran tests on the 1.3b model, scaling the sequence length from 512 tokens to 24, 2048, 4096, 8192, all the way up to 16,384 tokens.
Let me guess. The longer the sequence, the bigger the advantage.
Exactly. The trend is undeniable. The delta between XSA and the baseline grows consistently as the sequence length increases.
I'm trying to visualize the mechanics of why that happens. Is because as you feed more tokens into the context window, the tension to compress all that diverse, distant contextual information into a single aggregated attention vector drastically increases?
Right. You are squeezing more signal into the exact same bottleneck.
So when you have a tiny context of, like, 512 tokens, maybe the attention mechanism can afford to be lazy. It can waste some capacity reiterating the self-value because the contextual load is just light.
Exactly.
But when you have 16,000 tokens competing for representation in that final attention output, any capacity wasted on redundant, point-wise features is going to be devastating to the model's ability to recall distant information. XSA removes that bottleneck entirely, allowing 100% of the vector to be used for context.
That is precisely the reasoning the paper outlines. But there is another emergent property here that ties deeply into long context windows, and it involves something we see frequently in modern architectures, which are attention sinks.
Oh, this is fascinating. For the audience, standard attention sinks usually require prepending learned dummy tokens to the very start of a sequence. The whole idea is to give the softmax function a safe place to dump junk or undesired attention mass.
Right, and let's explain why the softmax function desperately needs that dumping ground in the first place. In causal attention, the softmax scores for a given token looking at previous tokens must sum to exactly 1.0.
Right, because it's a probability distribution.
Exactly. If an attention head is looking at the prior context and finds absolutely nothing useful for its current computation, it still has to allocate its probability mass somewhere. It can't just output 0.
Right.
So without an attention sink, it spreads that mass around to irrelevant tokens, which creates high entropy noise that dilutes the important contextual signals across the entire network.
So we explicitly add dummy tokens, essentially telling the model, hey, if you have nothing useful to look at, just stare at this wall.
Correct. But with XSA, something wild happens organically. Because the architecture mathematically removes the projection onto the self-value vector, the network realizes it can safely allocate all that junk attention score to its own diagonal. It can just look directly at itself.
Wait, I want to make sure I fully grasp the mechanics of this. The model learns that the diagonal is a free dumping ground because it knows that the XSA formula is going to cleanly snip that mass out a microsecond later during the orthogonalization step.
That is the beautiful consequence of the geometry here. Since XSA mathematically guarantees that the self-value vector is zeroed out of the final output regardless of how high the attention score on the diagonal is, the model learns to assign a 90% or even 99% attention score to itself when it wants to ignore the context.
That's incredible.
It just dumps the noise there, knowing XSA will act as a perfect filter.
So XSA is acting as an implicit attention sink. It gets all the noise reduction benefits of an attention sink without having to explicitly modify the input sequence with dummy tokens or, alter the KV cache mechanics at all.
And they proved this empirically. They ran experiments adding 0, 1, and 4 explicit learned attention sinks to both the standard baseline and the XSA model. Even when explicit sinks are introduced to level the playing field, XSA maintains its substantial loss margin over the baseline. Yeah, it proves that XSA is fundamentally improving the routing of information, not just masking a softmax artifact.
Okay, let's synthesize everything we've unpacked in this deep dive so far. What we are looking at with exclusive self-attention is a mathematically rigorous enforcement of the division of labor. By simply taking the attention output and explicitly orthogonalizing it from the self-value vector, subtracting the exact geometric projection, using 2 lines of element-wise PyTorch code, you eradicate the attention similarity bias.
And the empirical results back up the theory completely. It costs virtually nothing in compute time or memory overhead. It lowers training and validation loss consistently. And most importantly, for the practitioner scaling these systems, the performance gains over standard transformers scale positively with both parameter count and sequence length.
It's a rare combination of theoretical elegance and brutal empirical efficiency. It's the kind of paper that makes you want to immediately pause your training runs and inject those 2 lines of code to see what happens. But, as always in this field, solving one problem opens the door to entirely new paradigms and new questions.
Which brings up a final, quite provocative thought from the source material for you to ponder as you look at your own architectures. We've seen the undeniable efficiency XSA brings to pure language modeling by pruning redundant information pathways. But as we move toward multimodal systems where point-wise features might represent entirely different concepts, like a spatial pixel patch in a vision transformer, or a specific frequency frame in an audio model, let the geometric constraint of exclusive self-attention unlock even greater gains.
Or does it risk discarding critical spatial or temporal self-anchoring that those specific modalities natively rely on?
Exactly. That's the question.
That is a massive open question, and honestly, a thesis waiting to be written by someone listening right now. Thank you for joining us on this deep dive. I highly encourage you to pull up the paper, grab that PyTorch snippet, and experiment with it in your own pipelines. Until next time, remember, just because an architecture is standard dogma doesn't mean its internal matrix geometry is clean. Keep questioning the defaults.